Swayam Prabha. Digital India. Educated India.
Welcome to the third lesson of the 8th module, which is on combined stresses part 3. Now, in the last two lessons of this particular module, we have looked into that we have discussed several aspects of the combined loadings, and thereby we have evaluated the combined stresses in members when they are subjected to different forms of combined loadings. Now, we have discussed that if a member is subjected to axial load and bending, then what happens to the combined stresses, or if a member is subjected to a twisting moment and a normal axial force, then what happens to the stresses, or if a member is subjected to the combined loading actions of the twisting moment and the bending moment or the shear force, then what happens to the combined stresses. Those aspects we have looked into. Now, in this particular lesson, we are going to look into some more aspects of combined loadings, where if a pressure vessel, which we have earlier analyzed for the pressures only, now if they are subjected to the external forces like the axial pull or the compressive force, or if they are subjected to twisting moment, or if the whole vessel, a cylindrical vessel, is supported on two supports and thereby some bending is induced into the member, then in addition to the stresses that is being induced because of the pressure inside, what happens to when they are subjected to these external loads as well. So, we are going to look into those aspects in this particular lesson. Hence, it is expected that once someone goes through this particular lesson, one should be in a position to understand different types of combined loadings that the members are subjected to. And when we are talking about the different types of loadings different members are subjected to, it includes of course the aspects whatever we have discussed in the previous lessons, as well as the aspects which we will be looking into this particular lesson, and thereby we should be in a position to evaluate the combined stresses thus generated in members, and also one should be in a position to evaluate stresses in members due to different types of combined loadings. The scope of this particular lesson therefore includes, we will be looking into some aspects of the previous lesson, which we call as the recapitulation of the previous lesson part. Then it includes the steps to evaluate combined stresses in members for different types of combined loadings. Now, now we are in a position to more or less summarize that due to different kinds of combinations of the loadings, the individual loadings which we have seen in the previous modules. Now, if a particular member is subjected to different kinds of load combinations, then what are the stresses we have looked into in the last two lessons, and in this particular lesson we will be looking into some more examples with particular reference to the pressure vessels, and then we will be in a position to list out that what are the steps you will have to go through to evaluate the combined actions of combined loading actions in a member, and thereby evaluate the combined stresses. Also, we will be looking into some examples for the evaluation of combined stresses in members due to different types of combined loadings. Well, before we go into the aspects of the pressure vessels, let us look into the questions, the answers to the questions which I had posed last time. The first question was, how will you evaluate the combined stresses if the member is subjected to torsion and bending moment together. Now, in earlier cases we had seen the member subjected to the axial force and the bending, and in the last lesson we have discussed some aspects of the member subjected to twisting moment and the bending moment. Now, the question is that how you are going to evaluate the combined stress in a member if the member is subjected to the combined actions of the twisting moment and the bending moment. And in fact, let me discuss the other questions, the second question also along with this. The second question reads as, how will you evaluate the principal stresses in the member if the member is subjected to torsion and bending. In both the cases it is subjected to torsion and bending. The first question is how you are going to evaluate the stresses, the combined stresses, and the second question is how you are going to evaluate the principal stresses. Maybe I can answer these two questions together through this example. Now, if you look into this particular example which we have discussed last time, that if a member of circular cross section is subjected to a twisting moment, and this is a positive twisting moment whose vectorial direction is towards the positive x axis, and it is subjected to a load, this is a cantilever beam, and this load generates moment at this particular section. So, this particular member, the cantilever beam, is subjected to the action of the twisting moment T and a bending moment M at the section where this A and B is situated, and also because of this particular loading situation, this particular cross section will be subjected to a shear force B. Now, the stresses, if we look into at this particular section at point A and B, because of the actions of these individual forces, the twisting moment, the bending moment and the shear forces, the stresses that are generated because of the twisting moment T is the shear stress, which is given by T rho by J, and the direction of the shear stress as it is shown over here, because of this positive twisting moment we have the shear stress acting in this particular direction, and at point B it is acting vertically downward direction. So, these are the direction of the shearing stress at point A and B. So, that is the contribution of the twisting moment T in this particular member, and the bending moment which is getting generated because of this load P, M is equals to P times A, if we call this distance as A from the load point, then the stress is equals to My by I. Now, this bending stress is going to produce the normal stress, and at the top point from the neutral axis, if we take this radius as r, then the normal stress there is sigma x. Now, point B, since it is lying in the neutral axis, as you know, the bending stress is not going to produce any stress at the neutral axis, and therefore, the normal stress at point B will be equals to 0. Now, in this particular case, since we have the load P which is contributing to the shear force V, so therefore, we will have a component which is getting generated because of the shear force, and the shearing stress, as you know, is equals to VQ by IB, and the top of this particular member will not be subjected to any shear stress because of the shear force, but we will have the maximum shear stress at the neutral axis level, which will be occurring at B. Therefore, if we look into the resulting normal and the shearing stress that are occurring at A and B, they will be like this. At point A, we will have normal stress sigma x, which is getting generated because of bending moment M. We will have the shearing stress tau, which is getting generated because of the twisting moment, but this point will not experience any shear stress because of the vertical shear force V, and the point B will have these kind of stresses. Here there are no normal stresses because it is lying on the neutral axis, and we have only bending which is contributing to the normal stress. Therefore, this particular point does not have any normal stress, but there will be shearing stress because of the twisting moment T, and also you will have shearing stress which is getting generated because of the shear force V. So, thereby we will have a resulting shearing stress which is tau 1 plus tau 2 at this particular point. So, this particular point will be in a state of pure shear where we do not have any normal stress. So, these are the combined actions of loading because of the torsion and bending that is acting in the member, where we get these kind of stresses. Now, the question is that if we like to find out the principal stresses, now as we have done in the past, what we need to do is we need to plot these stresses in Mohr circle. Now, as you know that this is the positive sigma axis and this is positive tau axis downwards. Now, for the first case, if we plot the positive sigma x and negative tau, this is the point which represents that plane, and since we have sigma y as 0 and tau as positive, so this is the point which is representing the other plane. Now, if we join these 2 points together, it cuts the sigma axis at this point, which is the center of the Mohr circle, and with this O as the center and OA as the radius, if we draw the circle, the maximum normal stress which we get is this particular point, and this is the distance from the origin, which is sigma 1. We call this as the maximum principal stress, and the other point in the Mohr circle in the diametrical direction on sigma axis is the minimum normal stress, which is equals to sigma 2. Now, this is the state of stress at point A of the previous figure, and this is the state of stress at point B of the previous figure, where we do not have any normal stress, but we have the shearing stress. So, on right hand side plane, you do not have any normal stress, the normal stress is 0, but we have the shearing stress. Now, this shearing stress will have the value over here, 0 normal stress and the shearing stress tau 1 plus tau 2, and on the other side again you have 0 normal stress and negative positive tau 1 plus tau 2 in the perpendicular plane, and once you join this becomes the center of the Mohr circle. Thereby, the maximum normal stress which we get corresponding to that point B, this is equals to sigma 1, and as you have seen earlier, this value of sigma 1 is equals to tau 1 plus tau 2, the radius of the circle, and the minimum normal stress or the minimum principal stress which you have is equals to sigma 2, and sigma 2 also is equals to tau 1 plus tau 2. So, you see, you can observe now that the member which is subjected to the combined actions of the bending and the twisting moment, I mean the twisting moment and the bending because of the load, will be subjected to the combined stresses, and we can compute the value of the principal stresses using the Mohr circle, which we had discussed in module 1, where we had that if you have the biaxial state of stress, how to compute the principal stresses or stresses at any inclined plane with reference to the x axis at that particular point. And the third question was that what will be the value of the normal stress when on the neutral axis when the member is subjected to torsion and bending. Now, when it is subjected to torsion and bending, what will be the value of the normal stress along the neutral axis? Now, when the member is subjected to torsion and bending, as you can see that torsion is producing shear stress, which is T rho by J, and bending is producing normal stress, which is M y by I. Now, as you have noticed that bending stress in the cross section produce a linear distribution of the stress, and on the neutral axis the stress is 0. Now, since you do not have any other normal forces acting in the member, thereby when a member will be subjected to combined action of bending and torsion, the normal stress along the neutral axis will be equals to 0. So, it will be, if we choose a point to evaluate the stress which is lying on the neutral axis, then it will be subjected to shear stress only, and that will be in a state of pure shear, and it will not have any normal stress at that particular point when you are evaluating the combined effect of the stresses. Well, then having looked into these answers, let us look into the actions of the combined loading in a pressure vessel. Now, in the previous module or in module 3, where we have discussed the effect of pressure in a cylindrical or spherical pressure vessels, which is a thin wall pressure vessel, how to compute the stresses exclusively because of the internal pressure. And as we had seen that because the wall is thin wall, because of the pressure, the stresses which we get is on the wall, and they are in the circumferential direction and in the longitudinal direction. The stress in the circumferential direction we have called that as a hoop stress, and you have the longitudinal stress. Now, if such pressure vessels which are subjected to internal pressure because of the contained liquid, if they are subjected to some kind of external loading as well, as it is indicated over here, say the pressure vessel is subjected to a tensile pull P and also a twisting moment T externally, then what will be the consequence of the stress, say at this particular point A? If we are interested to find out the stress at this particular point A, because of these combined actions of the loading, then what will be the state of stress? Now, as you have seen that when we have the internal pressure, if we look into the effect of the loadings individually, what is the contribution of this individual loading in the stresses, then because of the internal pressure inside the vessel, we will have the circumferential stress or the hoop stress as PR by T. This we had seen it earlier. Also, the longitudinal stress is equals to PR by twice T, which is indicated over here. So, this will be sigma longitudinal and this is sigma circumferential. These are the contributions from the internal pressure. Now, let us look into the what will be the state of stress because of the axial pull P. When the vessel is being pulled by an external tensile pull, then every cross section of this particular vessel will be subjected to a stress, and this we have designated as normal stress, and that normal stress is nothing but equals to this tensile pull divided by the cross sectional area. Now, this being a thin walled pressure vessel, the cross sectional area as we had seen earlier is equals to twice pi r T, and the longitudinal stress contribution because of the axial pull is equals to P divided by twice pi r T. So, this is the normal stress that is getting generated because of the axial pull P. Now, this particular member also is subjected to a twisting moment. Now, here whatever we have indicated is a positive twisting moment, the vectorial direction of which is in the positive x direction. Now, this particular element, when they are subjected to this twisting moment on the surface, it will be subjected to the action of a shearing stress, which is given by T rho by J. Tau, as you know, is equals to T rho by J, and J for this thin walled cylindrical member is equals to twice pi r cube T, and R being the extreme radius of the top point or the point where we are evaluating. So, tau is equals to T r by twice pi r cube T. So, as you can see now that individually these three loading conditions, one is the pressure internally, another one is the axial pull, and the third one is the twisting moment that is acting. Individually they are generating sigma c is giving you the normal stress in the y direction, sigma L is giving you the normal stress in the x direction, also the axial pull is giving you the normal stress in the x direction, and the twisting moment is generating the shearing stress. So, the total normal stress that you have in the x direction, this is equals to the, this is the contribution of the pressure part from the internal pressure, and this is the contribution of the external pull. Now, here this should be a this is plus this will be the total stress in the x direction, and in the y direction we have the circumferential stress which is equals to P r by T, that is in the y direction. So, that is sigma y, and in addition to that we have the shearing stress which is indicated over here. So, this particular element now is subjected to sigma x, sigma y and tau. Now, as we had seen earlier in module 1 that if a particular at a particular point in a body, if we have a biaxial state of stress along with the shearing stress, then how do we compute the resulting principal stresses? We can compute the maximum value of the normal stresses which are given by sigma 1 and sigma 2, maximum and minimum principal stresses, and also the maximum value of the shearing stress we can compute from these combined state of stresses. Now, we can plot these values in the Mohr circle, and thereby we can get the values of the principal stresses. Now, since we have looked into different kinds of combined loading situation in members, in the previous two lessons you have seen that a member when it is subjected to axial pull and bending, then what is the combined state of stress. In the subsequently in the last lesson we have seen that if the member is subjected to a twisting moment and axial pull, then what is the effect, or if it is subjected to the twisting moment and bending, then what is the consequence in the combined stresses. And now that we have seen that if a pressure vessel is subjected to internal pressure along with this external loading, then how do we compute the stresses. Now, if we look into all these cases, more or less they follow a normal guideline or general guideline which can be listed out over here. You see, what we are interested to do is that we are interested to evaluate stress at a particular point in a body which is subjected to the combined actions of the loading. So, we select a point where we need to evaluate the stresses, and this selection of the points generally is selected at a particular point where we expect that stress level for some of the loading actions could be the maximum. Say for example, if we draw the bending moment diagram of a member which is subjected to bending, we know that where the maximum bending moment can occur. So, we can choose that particular point where the maximum bending moment occurs, and then compute the stresses corresponding to the bending, and also we compute the stresses corresponding to the other actions of the loading, and then we try to analyze that what will be the consequence of the combined loading action at that particular point. Likewise, we can select the point where we expect the maximum shear stresses will be generated, or where we have the maximum actions of the shear force, and then at that particular point what is the consequence of other loading actions, and thereby what will be the value of the combined stresses. So, likewise we select some points if we know the positions of the maximum loading situations like bending and shear, as I was describing, we select those points, or else we choose some points in the member, and then we try to find out that which one gives you the maximum of all these maximum situations, and that we treat as the worst situation for the load combinations or the combinations of the combined stresses. Secondly, what you need to do is that at that particular point, the point which you select, you need to determine the stress resultants. Now, what are the stress resultants? As we have seen, what is the axial force that is acting at that particular section where that point lies, or what is the value of the twisting moment at that particular section, or what is the value of the bending moment at that particular section, or what is the value of the shear force at that particular section, or if it is a pressure vessel, then what is the state of stress that is getting generated because of the internal pressure within that particular vessel. So, at that particular point we try to find out first the stress resultant, and then for each individual such stress resultant quantity, what are the consequences on the stresses. So, we calculate now the normal and the shear stress contribution of each individual load, including the stresses that will be generated in a pressure vessel, the normal stresses. Now, once we get the normal and shear stresses for each individual load, then what we do is that we try to combine suitably according to their signs, depending on compressive or tensile normal stress you have or the shearing stresses you have. We algebraically sum them up and arrive at what will be the resulting value of the normal and the shear stress at a particular point which we have selected to evaluate the stress at that point. So, combine the individual stresses to obtain the resulting normal and shear stresses. So, this is what is important. Thereby, we now arrive at two stresses. One is the normal stress, or rather three quantities: sigma x, sigma y and tau xy. Sigma x and sigma y are the normal stresses, and tau xy is the shear stress. So, at a particular point we arrive at these three quantities corresponding to, of course, the plane state of stress, and then once we get that, at a particular point, once we know that what is the value of sigma x, what is the value of sigma y, and consequently what is the value of the shearing stress, then we can plot them in the Mohr circle, or we can use the transformation equation, from which we can compute the values of the principal stresses and the maximum shear stress at that particular point. And once we know the stresses, then we can compute the value of the strain using Hooke's law. Now, these are the steps more or less which are common for all these situations which we have analyzed so far, or which we are going to analyze in this particular lesson. Now, wherever a member is subjected to such combined loading actions, these are the steps you will have to follow, so that you can arrive at what will be the consequence of this loading at that particular point in terms of the stresses. Well, then let us look into some of the examples on these combined loading situations. Now, this is one of the examples which I had given to you last time, wherein the actions will be in the form of bending and torsion. Now, here you see this is a sine board which is connected to a vertical member, which is a tubular member, and it gives the direction of a particular street. Now, here when this particular signboard is subjected to a wind pressure of 1.8 kilopascal. Now, what you need to do is you need to determine the maximum in plane shear stress at points A, B and C. These are the 3 points selected. This is the cross section of the vertical post, and this is let us say at the support point where we expect the maximum bending moment to occur because of the loading. Now, when wind load occurs perpendicular to this board, then the total load that will be exerted by the wind will be equals to the wind intensity multiplied by the whole area, and that is expected to act the resulting force at the center of gravity of this particular board. Now, this CG of the board being eccentric with respect to the center of gravity of this particular vertical member, so the loading to this member is eccentric with respect to its vertical axis. So, if we like to shift this particular load to the central axis of this particular member, this will be associated with a moment of magnitude. If we call this as load P, this load P will be shifted to the center P with a moment which is equals to P times E, and incidentally this particular moment P times E is about an axis which is lying in this plane of the tube, and this moment is nothing but a twisting moment to this tubular form. And since this particular vertical member is supported at the base and free at the top, it is like a cantilever beam which is subjected to a concentrated load towards the free end, and this load is going to cause a bending moment at the base which is equals to P times this vertical distance, and because of this P there will be bending at this level. Also this cross section will be subjected to the shearing force. Now, because of the bending there will be normal stress, because of the shearing there will be shear stress, and because of the twisting there will be shearing stress. Now, let us compute now that what will be the resulting stresses because of these 3 actions at point A, B and C. Now, before we go into the calculation of these stresses, one point you must note that point A is the top surface of this tubular form, and thereby when it is subjected to the shearing action, the shear stress because of the vertical shear force will be 0 at point A, and it will be maximum at the diametrical point BC, but the contribution of the shear stress in the twist from the twisting moment, you will have all 3 points will be subjected to the shearing stress. And when we talk about the normal stress because of the bending, A will be experiencing normal stress, but since B and C lies on the neutral axis, B and C will not experience any normal stress because of the bending. So, with this discussion, let us look into the calculation of the stresses at points A, B and C. Now, you see the analysis of this particular loading action is indicated over here, that you have the resultant load is acting at this particular point at the CG of this particular board, and this load is transferred to the vertical axis of the member, and this is the load P along with a twisting moment, and that is what is indicated over here. Now, this vertical post is subjected to a concentrated load P. Now, what are the distances? Now, this distance is 2 meter, and the diameter of the tube is 100 millimeter. So, if we shift this particular load to the center of this vertical member, it is 1 meter and this is 50 millimeter. So, 1.05 is the distance. So, the twisting moment T is going to be equals to this load multiplied by the distance 1.05. Now, how much is this load P? P is equals to the wind pressure which is acting on the board area. So, 1.8 kilopascal multiplied by 10 to the power 3, so much of pascal is the load acting on the which is distributed over the entire board, and the board area is equals to 2 meter by 0.75 meter, and that gives us a force of 2.7 kilonewton. So, this 2.7 kilonewton force which is acting at the CG of this particular board, if we shift it to the central axis of this tube, then we have the load P which is 2.7 kilonewton along with a twisting moment T which is equals to 2.7 into 1.05, which gives us a value of 2.8 835 kilonewton meter. Now, the concentrated load P, which is acting at a distance of, now the bottom of the board is at a distance of 3.2 meter from this support, and then the center line of this board lies at a half the distance between the two, which is 0.75 by 2. So, the distance of this particular load from the support is equals to 3.2 plus 0.75 by 2, which is equals to 3.575. So, M is equals to then 2.7 into 3.575, which gives you 9.653 kilonewton meter as the moment at the base level. And at this level, if you take a free body diagram, it is like a cantilever beam, you have a is having a load here. Now, if you take a section here, at this section you have the shear force B. So, B is equals to, I mean, if you take the free body diagram like this, you have the direction of the positive shear as this. So, V is equals to minus P, and this is what is indicated over here, that V is equals to minus 2.7 kilonewton is the shear force you have in the member. So, at this particular point, then the three quantities which are acting is the twisting moment T, the bending moment M, and the shear force V. And as I have told you that at point A, we will have the normal stress because of the bending, and we will have the shearing stress because of the twisting moment T, which we have called as tau 1. And since this is a vertical member, the tubular member is a vertical member, and the bending is going to cause a stress in the y direction, and so we have the normal stress as sigma y, but we do not have any stress in the x direction, sigma x is 0. So, this particular element A will be subjected to a normal stress sigma y and a shearing stress tau 1, which is getting generated because of the twisting moment T. But point B and C, which is lying on the neutral axis, will not have any normal stress, and we will have the shearing stress tau 1, which is because of the twisting moment T, and we will have the shearing stress tau 2, which is because of the shearing force V. So, if we compute the stresses now because of this moment, twisting moment and the shear force, then we get these values. Now, here you see that the shearing stress tau 1 is equals to T times rho by J, and J is the polar moment of inertia, which is given by this, J equals to pi d4 by 32 for this tubular member. It's 100 is the outer diameter and 80 is the internal diameter. So, this gives us a value of 5.8 into 10 to the power 6 millimeter to the power 4, and that if you substitute here, 50 is the radius because the external diameter is 100. So, the maximum value where you will get the shear stress maximum is R equals to 50, and this is what is used here. So, this gives you a value of 24.4 megapascal. This is the value of the tau 1. Now, the shearing stress tau 2, which is because of the shearing force which will be acting at this level, because at this point, at point A, the contribution of the vertical shear force is 0, because shear stress distribution, as we have seen, is 0 at the two outer surfaces, and you have the maximum value of the shear stress at this neutral axis position, and the value of which is given by this. When it is a solid circular one, we have only 4p by 3a, but for a tubular member it gets modified by this expression, which we have already seen while evaluating the shear stresses in a member. You know, if you remember that when we have evaluated the value of the shear stress in a solid circular section or a tubular section, where we could calculate only at the diametrical position, because at other position we cannot calculate because the section is not parallel to the y axis, and the value of the maximum shear stress which we had obtained at that particular cross section, it was 4/3 of shear force divided by the cross sectional area, and when it is a tubular section it gets modified in terms of those radii, and this is the expression for evaluating the shear stress. So, the shear stress which we get from the shear force is equals to 1.9 megapascal, and the normal stress which we get because of the bending, which is my by I, bending moment as we have seen is 9.653 into 10 to the power 6 so much of Newton millimeter. 50 is the extreme distance where we are computing the stress, and I is the moment of inertia, which is pi d4 by 64, and is 2.9 into 10 to the power 6 millimeter to the power 4. So, that gives us a stress of 166.43 megapascal. So, this is the value of the normal stress, this is the value of the shearing stress which we are getting for the twisting moment, and this is the value of the shearing stress which we are getting from the shear force. Now, with these stresses, now if we try to find out the resulting stress in the member, because we are interested to find out what will be the values of the shearing stress at point A, at point B and at point C, the resulting shearing stress because of these individual loading actions. And what are the loading, individual loading that is acting at that particular cross section at support? They are the twisting moment, the bending moment because of the eccentric loading, and the shear force because of the loading that is acting on that member. Now, as you have seen that we have obtained the value of the normal stress as 166.43, and the element on which we have sigma x is 0, sigma x is 0, sigma y we have as 166.43, and we have the twisting moment, I mean the shearing stress which is negative on this. Or at this particular point we have a positive shear stress as is plotted over here, that we have 0 value of the stress, and we have sigma y and the negative of the shear stress over here. So, this is the 24.4 is the shearing stress that is getting generated because of the twisting moment. So, if I join these 2 points, we get this as the center of the Mohr circle, and if we draw the circle, then these are the 2 points which gives us the value of the maximum normal stresses, the maximum principal stresses as we call it, and the radius of the circle gives us the value of the maximum shearing stress. So, if we compute now, as you know that this distance is 166.43 from here. So, this particular distance, if we call this as O, this as A and this as say A dashed, then the magnitude of O A dashed will be equals to as you know that sigma x plus sigma x minus sigma y by 2, and that is what is the half of that sigma x being 0. So, we get half that stress as the normal stress, and this is the shearing stress, and radius of this will be equals to this square plus this square, and this is what is indicated over here, that radius equals to 83.22 square plus 24.4 square, which is equals to 86.72 MPa, and that is the radius of this Mohr circle, and that gives us the value of the maximum shearing stress at that particular point. So, at point A, the resulting shear stress which we have from the loading actions is equals to 86.72 megapascal, and at point B and point C, as you have seen that we have shearing stress from twisting moment as equals to 24.4, and the shearing stress from the shear force we have as 1.9. So, if we combine this together, tau 1 plus tau 2 is the shearing stress that will be acting at B, which is equals to 26.3 megapascal, and at point C we have the difference of tau 1 and tau 2, tau 1 is acting in this direction and tau 2 is acting in this direction. So, the resulting shearing stress at C is equals to 24.4 minus 1.9, which is equals to 22.5 megapascal. So, you see then these are the values of the shearing stresses tau A, tau B, tau C at 3 points A, B and C, which are getting resulted from the wind load which is acting on that sign board. So, you see that when we are using such signs which are eccentric with respect to the vertical post, the vertical post is subjected to the actions of the shearing stress, and also of course, it is subjected to the normal, the maximum principal stresses as well, as you can see from this particular Mohr circle. Well, let us look into this particular example which is based on the discussion which we had in this particular lesson, where we have discussed the effect of the external loading on a pressurized vessels. So, here we have a pressurized cylindrical tank, that means it is subjected to the actions of internal pressure. Also, it is acted on by loads which is a tensile pull and there is a twisting moment. Now, the internal pressure given is 3.5 megapascal. What you need to do is that you have to find out the value of maximum value of this load P, axial pull P, so that the tensile stress in the wall of the cylinder does not exceed 70 megapascal. So, if you have to limit the tensile stress in the wall to 70 megapascal, then what will be the maximum value of this P? And the value of the twisting moment given is 500 Newton meter. The diameter of the tank is 100 millimeter and the thickness of the wall is 3 millimeter, and the internal pressure that is acting is 3 megapascal. So, as you can see in this particular vessel, we have three loading actions. One is that we have internal pressure, and that will give rise to the two stresses as we have seen. They are the circumferential stress and the longitudinal stress because of the internal pressure. Also, it is acted on by the axial pull, and because of the axial pull at every cross section, the member will be subjected to the normal stress, and the member is subjected to a twisting moment, and because of this twisting moment, the wall of the pressure vessel will be subjected to the shearing stress. So, you see there will be resulting normal stress, and the normal stresses will be generated from the internal pressure of the liquid and because of the axial pull of the vessel, and the shearing stresses will be generated because of the twisting moment. So, once we have the resulting normal stress and the shearing stress, then we can compute the maximum tensile stress that will be generated in the wall of the vessel. So, let us look into the computations of these individual quantities, so that we can find out what will be the maximum value of the tensile stress. Now, as you know that the circumferential stress or the hoop stress because of the pressure, internal pressure, is equals to PR by T in the thin cylindrical wall, cylindrical vessel. Now, P is given as 3.5 megapascal, which is Newton per millimeter square. R is the radius where you are calculating the stress, which is equals to 50 millimeter, the external radius, and T is the thickness of the wall. So, that gives us a value of 58.33 megapascal, and as you know, the stress in the circumferential direction is the y direction, and that is why we call that as the sigma y, the normal stress in the y direction. Now, in the x direction, because of internal pressure, there will be a stress which we have called as a normal stress, sigma L1, and that is equals to PR by twice T, and that is the internal pressure P, R is the radius, and 2 times the thickness will give us the longitudinal pressure or the normal pressure in the x direction. Also, because we have the axial pull in the pressure vessel, so it will be experiencing, this point will be experiencing a normal stress, and the magnitude of this particular normal stress will be equals to P divided by A, and P is unknown to us, and A of course is equals to twice pi r T for the thin walled hollow section here, where T is the thickness and R is the radius, the external radius, and tau xy, the twisting moment T will give rise to the shearing stress on the wall, which is equals to T rho by J, and J is equals to twice pi r cube T, as you know, for these hollow sections, and that is equals to 2.36 into 10 to the power 6 millimeter to the power 4. So, if we substitute the value of T is 500 Newton meter, so multiplied by 10 to the power 3 to make it Newton millimeter, rho is 50 millimeter, and J is equals to 2.36 into 10 to the power 6. So, that gives us a value of 10.61 megapascal, that is the value of tau xy. So, you have normal stress sigma x, which is the sum of the effect of the internal pressure and the external loading. You have the normal stress sigma y, which is getting generated because of the internal pressure, and you have the shearing stress tau xy, which is getting generated because of the twisting moment T. Now, if you have these stresses, the resulting combined stresses in terms of sigma x, sigma y and tau xy, because of internal pressure, the twisting moment and the axial pull. So, for all three loading actions, we have individually first computed the normal stress and the shearing stress, and now we have combined these normal stresses and the shearing stresses to find out that at that particular point, because of these combined loading actions, we have the resulting normal stresses sigma x, sigma y and the shearing stress tau xy. Now, if we make use of this to find out what will be the maximum normal stress at that particular point, then we plot them in the Mohr circle. We have the value of sigma x which is computed, and sigma x is equals to we have seen as 29.17 plus p by a, and probably as we can see from the previous one, that value of the sigma x is equals to 29.17 plus p by a, and value of sigma y is 58.33 and tau xy is 10.61. So, in this, then this is sigma x and this is sigma y. Sigma x and tau xy is indicated by this particular point, and sigma y and tau xy is indicated by this particular point. Now, if we join them together, this is the center of the Mohr circle where it cuts the normal stress axis, sigma axis, and this is the tau axis. Now, considering O as the center and let us call A as the OA as the radius, we plot the Mohr circle, and thereby this particular point gives us the value of the maximum stress or maximum normal stress, which we call as sigma 1, and this is the value which gives us the minimum normal stress, which we call as sigma 2. So, you have the maximum value sigma 1 is the maximum tensile stress, because it is a positive sigma. Now, from this particular circle, as you know, the centered distance from the origin is equals to sigma x plus sigma y by 2, as we had seen it earlier. So, the value of sigma 1 is equals to sigma x plus sigma y by 2 plus the radius of the circle. Now, the radius of the circle OA is equals to the OA square is equals to this square plus this distance square, if we call this as OA dashed. So, OA is equals to root of OA dashed square plus A dashed square. Now, OA dashed square is equals to sigma x minus sigma y by 2, and A dashed is equals to tau xy. So, this is what is indicated over here. You see 29.17 plus p by a is sigma x, minus 58.33 is sigma y. So, sigma x minus sigma y by 2 square plus tau xy square, this gives us the value of the radius, which is OA. Now, if you calculate this, it comes in this form, that p by 2a minus 14.58 square plus 10.61 square, and sigma x plus sigma y by 2 then is equals to 29.17 plus p by a plus 58.33 divided by 2, and that gives you a value of 43.75 plus p by twice a. Now, as we have seen that we have sigma 1 is equals to sigma x plus sigma y by 2 plus the radius r, and as it is indicated that this value of sigma 1, the maximum tensile stress should not be more than 70 MPa. So, if you take this as limiting value and if you substitute these values of sigma x, sigma y, we can get the value of p. Now, let us look into that. If we substitute the value of sigma x and sigma y, then what do we get? Now, here let us say we have sigma 1 as equals to sigma x plus sigma y by 2 plus the radius r. Now, sigma x plus sigma y by 2, if you substitute, this is going to be equals to 43.75 plus p divided by twice a. This is the value of sigma x plus sigma y by 2. Sigma x, as you have seen, is 29.17 plus p by a, and sigma y is equals to 58.33. So, that divided by 2 will give you this, plus r, as you have seen, is equals to p by twice a minus 14.58, the square of this, plus tau xy square, which is 10.61 square. Now, sigma, as we know, that is to be limited to 70. So, if we take this part on the left hand side, then it becomes 70 minus 43.75 minus p by twice a square of that. This is equals to root of this, we are squaring. So, the root goes up, we have p by twice a minus 14.58 square of that plus 10.61 square. Now, this part if you compute, you will have 20, this is 26.25 minus p by 2a square. So, if I expand this, we will have 26.25 square plus P by twice A square minus 2 of these two terms, which is P by A into 26.25, and this is equals to P by 2 A square plus 14.58 square minus P by A into 14.58 plus 10.61 square. Now, as you can see from here that P by 2A square term gets cancelled, and this if you take on the other side, you have P by A into 26.25 minus 14.58, and the other terms we can combine them together. Now, if you do that, if you take this minus this minus this, that becomes equals to 364, and this 364 is equals to P by A into 26.25 minus 14.58, and if you compute from this, you will get A, as you know, is equals to twice pi r t, and if you substitute the value of r as 50, t as 3, you will get the value of P as 29.4 kilonewton, and that is the load, that is the maximum amount of load that you can apply. This is what is written over here, that maximum value of the load is equals to 29.4 kilonewton that can be applied, so that the stress does not go beyond 70 megapascal. The maximum tensile stress in the vessel at that particular point should not go beyond 70 megapascal, and the limiting value of P is equals to 29.4 kilonewton. Well, let us look into another example, which is again related to this pressure vessel, where a thin circular cylindrical vessel is subjected to an internal pressure P, which is not known to us, and it is simultaneously compressed by an axial load of magnitude 72 kilonewton. So, if the allowable shear stress is 60 megapascal, then what will be the value of the maximum internal pressure? We will have to compute the value of the P max if the shearing stress is limited to 60 megapascal. Now, if we choose a point in the vessel wall, we can find out the value of the normal stresses, the longitudinal and the circumferential stresses, because of the pressure which we have said sigma L and sigma C, and this external force of axial 72 kilonewton will give compressive stress, compressive normal stress in the vessel wall. So, if we take the resulting of this, then we can find out that what will be the values of longitudinal stress and the value of the circumferential stress, and since here there are no shearing stresses acting, so these will be the principal stresses, and thereby we can compute the shearing stresses directly from them. Now, here you see that we have computed these values, and the value of the normal stress in the y direction, which we call as the circumferential stress, is equals to P r by t, and r being 50, t being 4, we have sigma y as 12.5 p. P is unknown to us, and the normal stress in the x direction, which is, or in the longitudinal direction, sigma x, we have called that as sigma 2. Because of the internal pressure, we will have the longitudinal stress as P r by twice t. Also, because you have the axial compressive load P, so at every cross section the normal stress will be equals to P divided by A, and since again it is a thin walled pressure vessel, so the area will be twice pi r t. So, since this that is compressive, P r by twice t is tensile and P by A is compressive, so that is subtracted. So, P times 50 is the radius times twice t minus capital P is 72 kilonewton and twice pi r t. If we substitute, we get a value of 6.25 p minus 57.3. So, this is the resulting normal stress in the x direction, and this is the resulting normal stress in the y direction. Now, here we do not have any external loading on the member which can contribute to the shearing stress. So, since there are no shearing stress at that particular point, so those normal stresses, as we know from the Mohs circle, the places where we do not have the shear stress, they are the principal stresses. So, here these are the values of the principal stresses, let us call them as sigma 1 and sigma 2. Now, as we know, the maximum value of the shearing stress tau max is equals to sigma 1 minus sigma 2 by 2, and as it is indicated in this particular problem that the maximum value of the shearing stress that we can go is up to 60 megapascal. So, if we have to limit the value of the shearing stress to 60 megapascal, then what will be the value of the P? Now we can compute the value of the shearing stress in terms of the sigma 1 and sigma 2 or in terms of P. Now sigma 1 is equals to 12.5 P minus we have 6.25 P plus 57.3. So this is the value of sigma 1 minus sigma 2. So that gives us 6.25 P plus 57.3, and that divided by 2 gives you the shearing stress, that's equals to 60. And from this if we compute, we get the maximum pressure that can be applied is equals to 10.03 megapascal. So because of this combined action, this is the maximum value of the pressure that can be applied inside the cylindrical vessel. Now we have another problem where a steel shaft of diameter D is subjected to a bending moment of 1.2 kilonewton meter and a torsion of 0.3 kilonewton meter. If the allowable tensile and shear stresses are 80 megapascal and 40 megapascal respectively, what will be the value of the diameter of the shaft? Now this problem is given to you. Look into this particular problem. We will be discussing about this particular problem in the next lesson. Well, then to summarize what we have done in this particular lesson is that we have looked into some aspects of the previous lesson, we have recapitulated the previous lesson. Now we have looked into some additional aspects of combined loading, and that is in the pressure vessel, and also we have looked into some examples to evaluate combined stresses in members after analyzing the actions of the combined loading. Now this is the last lesson of this particular module, and this module on combined stresses we had 3 lessons, and as you have seen in the lesson 1 we have introduced the concept of the combined loading, and also we have seen various forms of combined loading in members, and we had solved some examples which are related to the combined axial force and the bending. In the subsequent lesson, in lesson 2, we had looked into some aspects of the bending and torsion, and in the third lesson or the lesson which we have discussed today, there we have discussed some aspects of the combined loading in the pressure vessels. So that concludes us the lesson on the or the module on the combined stresses, and these are the questions set for you. How will you evaluate the combined stresses if the member is subjected to axial load and torsion? How will you evaluate the principal stresses if a pressure vessel is supported on 2 supports at a distance apart? And what are the types of loading a road sign is subjected to due to wind force? We will look into the answers of these questions in the next lesson. Thank you. Welcome to the first lesson of the 9th module, which is on stability of columns, part 1. In fact, in the previous modules we have discussed certain aspects of the stresses in members, and consequently we have looked into the effect of bending in a member where we have evaluated the deflection of the member. Now in this particular lesson we are going to discuss a different aspect, which is a stability of a member which we designate as column. Now it is expected that once this particular lesson is completed, one should be able to understand the concept of buckling of column members. In fact, we will define what we mean by column member, which member we term as column, and then we will look into certain characteristic features which we call as buckling. So buckling of column members under axial compressive load, and one should be in a position to evaluate critical buckling load in column members of different types. Now we will look into that what we really mean by critical buckling load, that the member which is subjected to axial compressive load, in which load is going to buckle or deform. The scope of this particular lesson therefore includes the recapitulation of previous lesson. In fact, the last module we have looked into the aspects of the combined stresses. We will look into the certain aspects of the combined stresses while answering the questions related to that, and this particular lesson includes the concept